Hi, and welcome to Technique FMC Tech Talks, where experts from around the company take you on an immersive journey into various industry topics, from equipment to processes, covering common trends and what's next. I'm Mike Robinson, and today we're going to talk about big bore gas. We're going to talk about gas projects. Traditionally, everybody thinks about the oil and gas industry, with oil being typically the, if you like, the biggest and the priority. But there are some unique and subtle differences when we're talking about gas. And what I want to do is take you through some projects that Technique FMC have been proud to work with the operators to develop for them, where we look at some gas projects around the globe. We're going to go to Norway, we're going to go to the UK, and we're going to go to Australia to touch on some of these. So the first one, as you can see on the screen right now, is you're looking at the Ormen Lange project in Norway. Ormen Lange is very interesting. If you're looking at this, the onshore, from onshore to the furthest away template on the seabed, you're looking at approximately 121 kilometers. So it's a subsea to beach. So the gas is being produced from around 850 meters. So that's 2,500 to 3,000 feet below the seabed. 2.5 below the sea level in the Norwegian North Sea, and then flowing through large diameter flow lines all the way up. And you can probably see on the screen there this large escarpment above my head, the Storgatan slide, where these pipes are going all the way up to onshore for that distance. So, and in the particular situation you're looking at here, you're looking at templates. So in this particular case, the reservoir for Ormen Lange was consolidated enough that they could actually get the drilling rig above these templates, and those templates could actually and will access up to 8 wells per template. So that makes it nice and easy and efficient for the drilling rig to drill and punch holes into the reservoirs to get the gas, and then bring them and consolidate them in through those manifolds into the large pipelines. Now, one of the things with gas that tends to happen is you tend to put a large amount of infrastructure down on the seabed initially, and then over time you populate the wells with gas, because the gas plants that receive the gas typically are set at a production level. So if you give them too much gas, they can't convert it to LNG. It needs to be within a certain range. So that's very typical. So when you, as I said, when you invest in a gas project, it's quite typical. You buy a lot of infrastructure on day one, but you may only put, say, 1 or 2 wells. So if you look at this faraway template over there, that initially probably only had a couple of wells installed in it. And then the template that's further down, as you see down here, down at the bottom, if I just go back there, that template again maybe only had a couple of wells, and then over 5, 10, 15, potentially 20 or even more years, they will incrementally add wells to that. So hopefully that makes sense. Now, as we look at oil and gas production, or as I said specifically gas production, what's one of the challenges with producing gas? And one of the challenges is liquids. A lot of gas reservoirs are driven by water aquifers from underneath. Okay, so there's water coming through. That water is essentially helping push the gas up, but the water is going to come through with the gas, and there may also be gas condensate, which is very good. Gas condensate typically has a higher value because it's the high-end liquid hydrocarbon. But if you start these wells up so quickly, the water that's associated with the gas and the condensate will come through it. You see it there mimicked through our flow manager system, representing how that gas could flow. If you cranked up those wells so fast, it's literally like blowing that liquid through the lines. Then what happens, it could blast all the way through 120 kilometers up to the gas liquid separators that you see, the slug catchers at the end, and you could actually fill up the slug catchers with liquid. No gas would be able to go through, and you'd actually have to stop the gas going into the gas plant, which is not a good day. Alternatively, you could start the wells up very slowly, and that is then inefficient. You're losing gas production. So then what you're really looking to try and do is optimize by switching on the wells in a sequenced way, using simulations, etc. And as I said, this is an extract from our flow manager simulation that has helped to optimize this to flow the gas back to the facility. So as I said, that's the Ormen Lange project. The other interesting thing about that one is the well bores. We talk about big bore. That uses 9 5/8 production tubing linked to a 7-inch inside diameter tubing hanger, then feeding into large bore manifolds and large bore flow lines, twin 30-inch flow lines all the way back. So gas tends to be larger bore to handle the bigger volumes. You potentially are looking at, say on Ormen Lange, some of these wells able to produce somewhere in the regions of perhaps 350 million standard cubic feet of gas per day, which is maybe twice as much as a good gas well in the US Gulf of Mexico. Now, where I'm going to take you to now is we're now going to go from Norway to Western Australia. So this is a project we did for Woodside called Greater Western Flank. It's a multiple different fields, and what I want to show you here is, unlike Ormen Lange where you saw all those wells gathered in one area below templates, this is quite different. And the fact that if you look at this original picture here, and I'll move out of the way a little bit so you can see the scale there, you're looking at about from the facility there at North Rankin all the way out to Lady Nora on your far right hand, my right hand side, is about 30 to 40 kilometres. So it's a very spread out set of smaller gas reservoirs that the Woodside, as the operator, were tying back in. So I'll pop that down and we'll just have a flip through. So instead of those big, large, complex 8-slot templates, you're seeing smaller, simpler inline T's and inline mechanisms. And then you're seeing single wells connected through mechanisms like these, plets, and then single flow lines, allowing us to get to single well applications that you see here. So here's a single well stepped out, tying into the flow line, and then we'll jump across and we'll see we're going further out now, and again another single well tied in this case single well here, and then over another well tied into the smaller manifold. So quite different. It's also large bore gas, meaning that the flow lines are quite large. But interestingly enough, on this particular application, because the well flow rates were lower than, say, Ormen Lange, which is in the, as I said, up to 300 million standard cubic feet, as I recall, Greater Western Flank was in the regions of about 200 million plus or minus million standard cubic feet. So it was right on the edge between what you would normally expect to use a 7-inch ID subsea tree for and a 5-inch ID subsea tree. And what was chosen to be done by Woodside in conjunction with us assisting them was to go for a 5-inch tree on this, because the gas wells would flow higher volume initially, and then they would eventually reduce their volume. But they actually used a 5-inch tree, but they opened up the choke and some of the manifold piping towards the manifolds and the flow lines to a larger diameter to accommodate those initial higher volumes. So they saved some cost by using smaller 5-inch trees and 5-inch infrastructure, but got the best optimization by using that, if you like, a nominal 6-inch style of outlet for it. So that's Greater Western Flank, just a quick look. If we then take another look at a project in Australia that we did that in some respects is quite similar to Ormen Lange, but of course it's similar, but it's different. And this was one project that we did for Woodside a number of years ago called Pluto. So Pluto is very interesting. It's a subsea to beach development. However, it goes subsea via a normally unoccupied facility. So as you see up there, you'll see we're looking at the subsea facility right now, sitting right here in about, again, 800 or so meters of water, and it is flowing up, see, if I remember correctly, about 15-16 kilometers to the normally unmanned facility. And then from the normally unmanned facility, it goes via a very long set of flow lines, perhaps in the regions of 140 kilometres, all the way to onshore the beach in Western Australia into an LNG plant. I'll pop up that little schematic, so hopefully you can see there at the bottom, you'll see the main Ormen Lange facility. It's going up from deep water. It's then going to go up the flow lines to the normally unmanned facility, and then you see the curved flow line, which is avoiding geological hazards and other challenges going onshore to Western Australia for gas to be turned into ultimately LNG. So as we pop that down, we'll look. So again, it's different from Ormen Lange. It uses clustered trees around a central large manifold. Those trees again are 7-inch inside diameter with 9 5/8 tubing, okay, feeding into large diameter flow lines and pipelines that go all the way up. It's round trip piggable so that they can actually send pigs down to sweep and clean and remove water. Again, like Ormen Lange, it has liquids associated with it. Those liquids are water as well as condensate. And we're using in this particular application here, these are vertical trees, 7-inch vertical trees. One of our earlier designs, our new 2.0 vertical tree system's a lot smaller and more compact than what you see there, but this is talking about the principles of gas. Ormen Lange is a horizontal tree versus a vertical tree, different applications, different customer preferences being used. And that's part of what we're looking at here. You see the main parts of the technology. I'm just going to flip on and jump across and zoom in quickly as that high level look. So you see the large diameter pipes, large diameter flow lines, and then we're going to go through an end termination. This was a tie-in that was added, so approximately, let's say, halfway along the flow line, slightly shallower water. Oil and gas operator were able to extract some additional reservoir and teed in. They had an existing tee into the pipeline, and then this is the view back the way now from the normally unmanned facility, looking back down the slope towards the Pluto subsea system. So that's Pluto in Western Australia, so similar but different to Ormen Lange, similar but different to Western Flank. If we then now take you, as I promised I was going to take you to the UK, we'll take you to a project in the UK. Once I find it. So this is a project we did a number of years ago, and of course it's a gas project, so it's still continuing. This is a project for Total called Lagan Tormore, which now has some additional reservoirs being added to it. Lagan Tormore again is a subsea to beach development. So if you look in the distance there, that facility onshore in the west of Shetland, in Shetland is a gas plant, and that's again around about the furthest distance away is approximately 120 to 140 kilometers. And again, in this situation, we have templates like Ormen Lange. We have templates, and these templates can contain 6 wells. But you also notice that far over here is an individual well, a satellite well, which is further away from the host. So we can tie in a satellite well as well. And then you also see in shallower water up the escarpment there, or up the edge there, some other wells that have been added. That's additional developments to Lagan Tormore. So 6-slot integrated template structure. These were designed for some of the conditions in the UK North Sea, so they are capable of withstanding potential fishing applications, so they're more protective versus the deep water Western Australia that were in deeper water and didn't require that application. And then you come up here, you see the large 6-slot integrated template structure. Let me just pop up a picture so you can see what that looks like in scale. So I think if you look very hard in the bottom sort of right-hand corner of that picture, you'll see a gentleman somewhere around there working in our facility. And so just imagine there, let's say approximately 1.5 to 2 meters tall, you maybe get a scale for that large template structure. And again, and that's the reason that the operator Total was able to build template structures like that is because they could access the reservoir from those 6 wells, 6 slots. The reservoir's large enough to access that, but they have the satellites for when those smaller reservoirs are further out. So as we continue to look, and we just look there again, smaller inline structures, there's a satellite well, and we'll not jump on this. There's some other very interesting things about Lagan Tormore. As I said, there's the 5-inch, it's a 5-inch vertical tree, given the flow rates. Now interestingly, and again this was done a number of years ago, but Lag & Tormore chose to use primary communication to the control systems that operate these units using fibre optics. So they use copper connections for power to provide power to the multi-phase or the wet gas meters, as well as the subsea control modules. But they also, the primary signal that actually commands and tells the systems what to do, and also feeds back information from the subsea system, is using fibre optics. And you see a little bit of a representation from that there. So that's taken you from, I started in Norway at the start, and then we went to Western Australia, a couple of projects, and then we've now come back to the UK looking at differences with gas. We've touched on 7-inch subsea trees, 5-inch large bore connections. There's a lot more detail we could go into, so please like what you see, come back and look and ask questions and ask for more, and we'd be happy to go into more detail. So thanks very much indeed for your time. That's it for me. Bye now.